Good morning, students. This is Dr. Anton Seviluis, working as an assistant professor in the Division of Aerospace Engineering from Karunia University of Technology of Sciences. And this is my second lecture in this online video lecture series. So in this lecture, I'm going to explain about the first law of thermodynamics and related topics in it. So I have a few slides in order to explain those topics, and maybe here you can see I have highlighted those topics, especially the heat and work transfer, and the sign conversion, and the examples of uh, heat and work transfer. Okay, fine. So first of all, the topic, the energy transfer by heat and work. Okay, so energy transfer. Energy is nothing but the capability of doing certain work. Okay, and work is nothing but external force. If there is an external force acting on a body or acting on a substance which moves in a certain distance, we call it as work. Okay, right? So there is a difference between work and energy, and this is work transfer. Okay, then afterwards we can see what will be the heat transfer. Okay, right. So in this work transfer, so it is a basic mode of energy transfer in a thermodynamic approach. Okay, so in a thermodynamic approach only we are discussing about this work transfer. Okay, right. And generally in mechanics, okay, in a mechanics approach, the action of a force on a moving body is identified. Okay, that can be identified as a work, right? And maybe in the equation format you can see the product of force and the distance moved parallel, as I mentioned now, the magnitude of mechanical work we can call it as. But in a thermodynamic approach, okay, in a thermodynamic approach, the work transfer is considered as occurring between the system and surrounding. Okay, so in a thermodynamic approach, most of the time we used to say as system. Okay, we will be considering the whole, universe, separate systems, and what is system and surrounding. I mean, in thermodynamic system and thermodynamic surrounding, right? Okay, fine. And so the work is said to be done by a system if the sole effect, okay, sole effect, generally the work in the sense of, I mean, if there is any, for example, if we are applying a force in a body or in a system or in a substance, that force, I mean, it should be enough, okay, to push the system in a certain distance. Okay, certain distance. So we are applying the pressure force. So that force will be converted as a displacement. Okay, that force will be converted as a displacement, and we can say it as a, there should be a certain amount of work has been done. Okay, so that is an example point of view. I'll be showing a picture you can understand easily. Fine. And in a unit wise, it is considered as Newton meter, otherwise Joule. We already solved the number of problems in it. Okay. So now, so here you can see in the pictorial explanation about work transfer. Okay, work transfer, right? It is not only a work, it is a work transfer from the system to the surrounding. Okay, maybe in the first example, it is indicated as there is a battery power source, and that power is connected to the electric motor, and motor shaft is connected with the fan. Okay, so the fan is situated in the surrounding, and rest all things, the motor and battery are situated in the system. Okay, so those things, those two things we are considering as a system, and the fan is only of the system, it is in the surrounding. Okay, and in the second picture, we are just replacing the fan with the pulley. Okay, so pulley rotates, so that is hanging with the weight. Okay, that weight will be moving up. Okay, we are pulling, I mean the pulley is just pulling the weights upward. Okay, so there is a certain amount of work has been done in a surrounding from the system. Okay, so the work transfer is takes place from the system to the surrounding, right? And in the second, I mean the third picture, you can see the battery alone we are considering as a system, and rest all things. Okay, the motor itself of the system, it is situated in the surrounding. Okay, right? And along with the pulley, and pulley is carrying the weight. Okay, the weight has been lifted, right? Okay, so you can see in the paragraph, the hence the word appears at the boundary. Okay, something which appears at the boundary. Okay, right? So because the boundary is situated in between the system and the surrounding. Okay, so it is mentioned at the boundary. Okay, so here it won't be within the system or exclusively of the system. It is at the boundary under the action of force. So the force is applying in the system, and the response is taken place in the surrounding. Okay, another definition, you can see the work is said to be done by system if the sole effect on things. Okay, sole effect is the third picture you can see. Okay, third picture is exclusively explaining about the sole effect. Okay, alone, the pulley alone is doing certain weights. Okay, and before discussing about the PDV displacement work, it is necessary to understand about the sign conversion. Okay, sign conversion for the work done by the system, work done on the system. Okay, I think we already discussed about the sign conversion. We know very well the work done by the system can be taken as positive. Work done on the system, that will be negative. It is exactly matching with the physical approach, physics. But in the chemistry, it will be different. Okay, you might have already studied in your school days. So two things. We can take it as the best example of this gas along with the reciprocating piston in a closed expands, the expanded gas is pushing the piston forward. Okay, expanded gas is pushing the system, I mean piston forward. So the gas is expanding because of if you are applying or if you are adding a heat. Okay, that is secondary, we won't consider. So the gas is expanding. Okay, because of that expansion, okay, it is a kind of positive expansion, because that if you are considering a W equal to rho dV, I mean W equal to P dV equation. So the dV, that is the expansion of the gas, the volume. Okay, volume is expanding, right, from one point to another one point because of that expansion, which leads to pushing the piston forward. Okay, so the work done by the system as a work done by the system. Okay, so maybe in this paragraph also you can refer. So it is clearly mentioned the work done by the system is usually considered as positive. Okay, why it is considered as positive? Because it is the work done is the path function. Okay, work done, heat transfer, both are the path functions which we already discussed. And change in state, change in state takes place from V1 to point V2. Okay, change in those are the point functions, volume. Okay, change in state takes place positively. Okay, and that is a work done by the system, work done by the system. So that we can consider, we can have the same approach. Okay, but in this time the gas is not expanding. We are the same the cylinder setup we can consider. Okay, the same system we can consider, and we are applying the force from externally. Okay, we are applying the force to the piston externally. Okay, so what will happen? The piston will be moving backward. Okay, the piston is moving backward. Okay, and the volume is reducing. Volume of the gas is reducing. Okay, so in the equation format, if you are writing W equal to PdV, so the initial will be greater. Okay, V2 minus V1. v2 minus v1. If you are taking in that case, you will be getting a negative sign. Okay, and the work done, it is off. We are applying force externally, so it is on the system. Okay, so you can see here in the paragraph, work done on the system paragraph, work done on the system is typically considered as negative in thermodynamics. Okay, right? And when compressing a gas in a piston, work is done on the system by an external force. Okay, I hope you understood. Yeah, now come to the PDV. Okay, so we can say it as a, it is also coming under the work transfer category, and it is the displacement work. Okay, same. Maybe you can see this picture PDV. Okay, so P1 V1, and once it is expanding, it becomes P2 V2. Okay, so in equation format, how can we represent? Okay, so along with we have a PV graph. Okay, PV graph, and how this is, I mean the state. Okay, state has been changed. Okay, right? And we can say as a point function p point 1 point 2. So the pressure, volume, those are the point functions, and the work transfer or work done takes place in the curve itself, and you can see how much work done has been takes place in a shaded. Okay, and we are specifically there is a infinitesimally small area in the picture you can see. Okay, so coming into the paragraph, when the piston moves an infinitesimal distance, okay, this infinitesimal word will be coming again in the FEA. Okay, FEA and finite element. Okay, right? It is very small. Okay, that's what the quasi-static process. I mean quasi-static word also we are using here. Okay, right? Without disturbing. Okay, very small, very slow process. Okay, the quasi-static process. Fine. So coming into this paragraph, when the piston moves an infinitesimal distance dl, okay, so that is a very small distance without disturbing the equilibrium. And if a, we are considering as a work done, okay, by the gas on the piston. Okay, this is during expansion, right? So that can be represented as F into dl, that is equal to PA dl. So A dl is nothing but A is the area meter square and dl is the distance meter, so meter cube. So P dv. Already I think you might have remembered the first module. Okay, fine. So similarly, when the piston moves out, okay, moves out from position 1 to 2, okay, 1 to 2, the volume is changing from V1 to V2, okay, and the amount of work has been done. So we can again represent W1 to 2 equal to V1 integral V1 V2 PDV. Yeah, and now you can see this graph. Okay, under the magnitude of the work done. Okay, magnitude of the work done. That's what we are calling as a work done is a path function. Okay, path function. We won't represent W equal to, listen carefully. We won't represent W equal to W2 minus W1. Okay, that is not a point function. W is the work done is not a point function. It's a path function. Okay, we should not represent W2 minus W1. I think someone asked a doubt about this thing. Okay, I hope it has been clear. We should not write W2 minus W1. Okay, in terms of point functions only we can write. Okay, that is the statement. Fine. So you can see the work done is given by the area under the path. Okay, under the path 1 to 2 path function. And it is shown in the picture. Since P is at all time a thermodynamic coordinate, all the states pass through the by the system as the volume changes from V1 to V2 must be equilibrium state. Okay, must be equilibrium state as well as must be quasi-static. Okay, quasi-static, right? Infinitesimally small or small slowest. Okay, right. And yeah, you can see here in the second paragraph, it's a process that happens at an infinitesimally slow rate. Okay, right? And yeah, also the quasi-static process is one in which is in thermodynamic equilibrium with its surroundings at all time. Okay, fine. So now come to the heat transfer. Okay, we know very well if the heat is added, it can be considered as a positive sign, and heat is rejected or heat is exiting. Okay, that is considered as negative sign. Maybe in the picture also you can see. Okay, so this is also coming under the energy transfer category, but in heat transfer. Okay, right? So heat is nothing but it is the estimation and transferring from one body to another body. Okay, one body to another body, right? So you can see form of energy. Okay, so it is the form and transferring across, okay, one body to another body in the sense across boundary by which you have a temperature difference. Okay, right? So there must be a temperature difference, then only the heat transfer takes place. Okay, if the temperature is equal, we cannot say there is a heat transfer. Okay, right? Heat is constant, heat transfer is constant. Okay, and if it can be represented as Q. Okay, we already solved the problem in the non-flow processes. Okay, so fine. And the temperature difference is the potential. Okay, temperature difference is the potential or force, we can say temperature difference, and heat transfer is the flux. Okay, fine. Yeah, you can see here. Maybe conduction, convection, radiation. Okay, if it is directly connect, I mean, if two systems or two bodies, two substances, two solid bodies are contact directly. Okay, there is a conduction. Okay, right. Okay, so you can see the explanations in these paragraphs. Yes, now come to the sign conversion, as I said. Okay, in the picture also you can refer. So heat flow into a system is taken to be positive and out of the system is negative. Okay, right? In the letter of Q we can represent, and this is also a path function. Okay, right? And yeah, you can see here it is a boundary phenomenon since it occurs only at the boundary of a system. Okay, only boundary of the system. If it is occurring within the system, we cannot say it is a heat transfer. Okay, across only is called a heat transfer. Okay, yes. So now come to the other type of work transfers. Okay, other type of work transfer apart from heat transfer. Okay, work transfer already we discussed the basic work transfer and other type of work transfer. It is coming under this category, around five, six types are there, but we are going to discuss only two or three. Okay, right, from the syllabus. So first of all, first thing is the electric work. Okay, so electric work, again it is along with the shaft work, all will be relating with the existing, the previous raising the weights. Okay, because we already discussed about the DC motor, electric motor. Okay, electric motor. So the electric motor is connected with the a pulley, and the pulley is holding the are carrying the weights. Okay, once the shaft rotates, that means the motor rotates, the shaft is driving the pulley and the pulley is lifting the weights. Okay, the same thing which is connected with here. Okay, but the difference is we are considering one element as a system. Okay, maybe in the picture you can see in this slide, the picture you can see the one element is nothing, it is we are considering as a resistor. Okay, maybe you can see here current. Okay, the current I. Okay, current is flowing through a resistor. Okay, so resistor is nothing but it is limiting, okay, resisting the current flow, right? So with the color code you might have seen, and we don't want to go much in deep about the resistor. Okay, right? So the current flows through a resistor taken as a system. So we are taking alone, I mean the resistor alone as a system. Okay, and there is a work transfer. Okay, work transfer into the system, right? And this is because of the current can drive, because this current can drive the motor, and the motor is connected with the pulley is holding the weight. Okay, so right. So in this approach we can take this. Okay, this electric work. Okay, the work done because of the electric electricity, we can say. So the current flow we can take it as I, okay, ampere, and that can be given as I equal to dc by t tau. Okay, so it is C is nothing but a charge, okay, right? Maybe a capacitive charge or something like, and in coulombs units, and the tau is in seconds, okay, the time, right? And so the DC is the charge crossing a boundary, okay? So that charge is crossing, okay? The boundary is nothing but it is mentioned in dotted lines, okay? You can see we are considering the resistor alone as system. Okay, there is a charge transfer takes place across the boundary, okay, during the time d tau, okay, right? And we are considering E is the voltage potential, like how we are representing that the force, okay. So here in electric work we are considering this E is the voltage potential, and the work can be written as dw equal to E into dc, okay, E into dc, and we already have an equation I equal to dc by d tau. So from that equation we can take it this dc, okay, dc we can rearrange dc equal to I into d tau. So that becomes E into I into d tau, and in integration, I mean, if you are integrating it from 1 to 2, okay, so you can write W equal to, okay, and if you are subtracting, I mean, if you are dividing by the d tau, the time, you can get it the power, okay. So that is a work equation, and the power equation will be W equal to limit d tau tends to 0, dw divided by d tau, okay, which is nothing but EA, that's all, okay. So that is electric power, you can get it. And similarly the shaft work, okay, that is the previous one is the electric work, and this is the shaft work, okay. So only so since it is a shaft work, we are considering only the shaft from the motor, electric motor, as a system, okay. Only we are considering the shaft as a system, and the shaft, maybe that shaft will be connected with the pulley, and the pulley is raising the weight, right? You can see here. So the shaft will be rotating in certain RPM because of the electric power. The electric motor is driving the shaft. Okay, right? So there is certain RPM, it will be rotating. There is a torque. Okay, torque is applied from the DC motor. Okay, so we are representing if T is the torque applied to the shaft, and DQ, I mean D theta. Okay, that is the angular displacement. Okay, so that shaft work can be written as torque into d theta, okay, torque into d theta, and the power also, that is a work done. Similarly for power we can write W dot, okay, power equation T dq by d tau, and that will be leads to T into omega, that is angular velocity. Equation T is considered as a constant, okay. So in this manner we can write the shaft work. And similarly we can have a steering work, okay. So you can refer it. Similarly I will be adding a few more works, okay. So you can refer, and related problems we can solve, okay, right? So this is nothing but here the stir, maybe like we have the egg stirrer, okay, right? Similarly the stirrer has been connected with the what do you call this kind of um, spring, okay, spring arrangement, and that is connected with the weight, okay. So once you leaving the weight, creating inertia force, okay, that will try to rotate the stirrer, okay. So that is stirring the system, okay, which is the closed system, okay, which is closed system, and there is a constant, I mean constant volume, okay, constant volume, right? So we are considering the mass is the weight, okay. So corresponding things you can see, and there is a datum, there is a vertical distance, okay, dz. So the equation is seems like a potential energy equation, okay, and we are correlating with the torque, okay. Torque will be applied in the shaft stirrer, in the stirrer, okay, and angular velocity also there, okay, right? Fine. So that's all about this lecture, and